Hello and welcome to this lecture. In the previous lecture, we saw some very interesting and simple properties of probability spaces, right. So, notice how the theory is slowly developing, right. So, we had the basic ingredients in the theory first, and then we just gave it a couple of axioms, and then we looked at events and how events can be manipulated, and look at how all the properties are sort of entering naturally into the game, right. So, what happens when you do unions, intersections, complements, what happens when one event is inside another event, it's sort of implied by another event and all that. So, it just quickly becomes very interesting, and that is one of the features of many of these mathematical theories. You start with something very simple and suddenly you will start getting very interesting answers, and probability is certainly like that. And what we are going to do next is take some simple examples. Some of them will be very simple examples, some of them will be slightly more complicated examples, and we will start using these properties, right. So, we will start working with the events in these probability spaces, start understanding what kind of probabilities they can have given the information, how do we use it, how do we use the properties and deduce something more interesting, etc., etc. Okay. So, let us get started. So, we are going to start with something very simple. We have been talking about it quite a bit, and let's see how probabilities work in this very simple probability space. So, this space is basically tossing a coin. The experiment is tossing a coin, and we know there are two outcomes, heads and tails. I am going to denote them as capital H and capital T. Okay. So, the sample space is something we have seen several times in this course already. It has got just two entries in it, set with two elements, capital H comma capital T. Okay, that is it. Now, what are the events in this sample space? Like, for instance, how many events are possible, etc. So, one can see that there are 4 events, right. So, that they make I mean, it's interesting to consider these 4 events. These are the 4 events, like the empty set, the subset which contains just one outcome, which is heads, right. So, I am going to call that event as E. Okay. Another subset which contains the other element, which is T, and then the entire sample space itself, H comma T. Okay. So, there are 4 events, and now let us see what kind of values the probability function can assign to these 4 events, right. So, for the entire sample space, you have to assign 1, right. P of S is 1. From the empty set property, P of E is 0. Okay. Already 2 probabilities are taken care of. Okay. Notice how the properties just enter the picture and simplify the work for you, right. Now, complement property is again interesting, right. So, you notice quickly that F is E complement, isn't it? You define E, which is heads, E complement is F, right. So, what is not in F, what is not in E but is in S, is that is the complement, isn't it? That is F. Okay. So, P of F better be equal to 1 minus P of E. Okay. So, the probability function, when you toss a coin, that experiment, if you start thinking of 4 events, then you want to assign probabilities for these 4 events, the probability function has to look like the following. Okay. You can assign whatever number you want for the probability of heads. Okay. Maybe we call it small p. Okay. Right now, I do not know what value to put for it. So, let us say we keep it as some p, unknown p. It is between 0 and 1, I know for sure. And once you assign that value, everything else gets taken care of. Why is that? Anyway, P of S and P of V were known before 1 and 0, no problem. The only thing that was left was P of E and P of F. If you put a value p, small p to P of E, then what should be P of F? 1 minus p, right. So, that comes from the complement property, that is it. So, if you were to actually apply this probability space to study the tossing of a coin experiment somewhere, you have to choose a value p. Okay. How do you do it? One way of saying is that maybe ahead of time that you know that the coin is fair. Okay. If the coin is fair, then P of E should be equal to P of F. Now, how do you make P of E equal to P of F? You have to equate P to 1 minus P, which gives you P equals 0.5. Okay. So, assigning a probability of 0.5 to heads and 0.5 to tails takes care of the probability space when you have a fair coin. Okay. So, a very simple example. I mean, I did not do anything very different or unusual here, just took a very simple sample space, looked at all the events that you can have. There are only 4 events in this very simple space, and looked at how is it that the probability function will work. Okay. And we got this very simple and very interesting idea that the only thing that matters, only thing that is in your hands, so to speak, is this small p, right, the probability of heads. Once you fix that, everything else gets fixed in the probability space. You do not have any room for playing with anything else. Okay, and we saw how if you want a fair coin, you want to put small p to be 0.5. Okay, so this is a very simple space. Hopefully this was clear, and you can see how the theory and the practice sort of meet somewhere, right? And then when you want to assign actual probabilities, you have to use some ideas that you expect from the practice or reality of the situation, some pattern that you may know, and then you get a nice probability space to work with. Okay. Now the next one is a bit interesting. By the way, all these examples I have taken from the book by Deepayan Sarkar, Siva Atreya and Steve Tanner, the book that's in preparation. You can go and read what they have written also about these problems. These are good to get used to the probability space and different ways of thinking about it. So here's a completely different sort of example, very different from maybe the tossing a coin example. Okay. So here's the situation, here's the experiment, so to speak. A certain restaurant wants to hire a waiter and a cashier. Okay, so and they maybe put out an application or advertisement in the paper, and some 4 people have applied. 2 people who I'm calling David and Megha, they're from Delhi. Okay, and then 2 others, Rajesh and Veronica, say are from Mumbai. Okay, so there are 4 people, and they are 2 from Delhi, 2 from Mumbai. Okay, so the restaurant is going to do a random experiment sort of thing in the hiring. It knows anyway. I mean, these are positions for which you maybe you can, all of them are equally qualified and well. I mean, they can be waiter or cashier in this restaurant. So they just decide to choose at random. Okay, so they're going to hire one person at random first as the waiter, and then there'll be 3 people left. From the remaining 3 persons, they will choose another person at random and make them cashier. Okay, so first person at random as waiter, and then from the remaining 3, you select one and at random make them the cashier. Okay, so for this experiment and scenario, the outcomes that are interesting to us, what are the outcomes? So let me just start writing out the outcome. Okay, the experiment is this random choice, right? The outcome is let's say waiter comma cashier, isn't it? Or let's say the name of the waiter, the name of the cashier, who got hired as the cashier, who got hired as the waiter. So that's the outcome. It's a very easy way to represent the outcome. So for example, you may have David selected as the waiter and Megha selected as the cashier, right? So that can happen, right? So David comma Megha might be one of the outcomes of this experiment. Okay, so how many what would be the sample space? Sample space is going to be the set of all possible outcomes, isn't it? So it could be David comma Megha, it could be David comma Rajesh, it could be David comma Veronica, and to save space, I'm only going to write the first initials. So they're all different initials, so I'll only write the first initials for the remaining folks. Okay, so David got hired as waiter, and then each of the others, one of the other 3 got hired as a cashier. It can also happen the other way around, right? So we'll be careful about it. Let's just write it first in any way, and then we'll come to it. Then you could have Megha hired as waiter, and then David hired as cashier. You can have Megha hired as waiter and Rajesh hired as cashier. You could have Megha hired as waiter and Veronica hired as cashier. Okay, right? So this is how it's going to look. And then you have the same thing. You can have R comma M, R comma, oh sorry, it's R comma, let me just, could have R comma D, R comma M, and then R comma V, right? And then you can have V comma D, V comma M, and then V comma R. Okay. So this is a sample space. It has all the 9 possible outcomes. Okay, all the 12 possible outcomes. Sorry, counting has gone wrong. All the 12 possible outcomes of who gets hired as waiter and who gets hired as cashier are written down here. This is the sample space. Okay. Now, the question asks for events. The first event is A, which is cashier is from Delhi. Okay. So, if the cashier is from Delhi, the cashier needs to be either David or Megha, isn't it? Okay. So, the event A is basically is the set David comma Megha, right. So, that qualifies for that, and the cashier is from Delhi. So, David is from Delhi. So, M comma D will also qualify, and then R comma D, R comma M, and then V comma D, V comma M. Is that okay? So, you have the cashier being either Megha or David, and the waiter we do not care, right. The waiter can be anybody else, and that gives you 6 possibilities for the cashier to be from Delhi, and that is the subset of that is the event A, which gives you the cashier from Delhi. Okay. Then next event B is exactly one position is filled by a Delhiite. Okay. So, these are all sort of problems where you have to write out a set given the description of it in English, right. So, exactly one position is filled by a Delhiite, right. So, you should have exactly one. So, it cannot be David comma Megha, it can be David comma Rajesh, it can be David comma Veronica, it cannot be M comma D, right. So, then both of them are filled by Delhiites. So, it can be M comma R, M comma V, and then it can be R comma D, R comma M, and then it can be V comma D, V comma M. Okay. So, the event A is that the cashier's position was from Delhi, did not care about the waiter position. The second one is exactly one of the two positions is filled by a Delhiite. Okay. Event C is neither position is filled by a Delhiite. So, neither David nor Megha should appear anywhere. Okay. So, you can have R comma V or V comma R, right, that is C. Okay. Both have to be either Rajesh or Veronica. Okay. So, hopefully this gave you one more view of how one works with probability spaces. It's a simple example, small example, but hopefully illustrative. You had an experiment where something happened at random, and then you had to write down all the possible outcomes into a sample space, and then you had to identify some events which were described in English, and then write it down precisely as subsets of the sample space. Okay. So, hopefully this example was also interesting. It's not, doesn't quite use the properties of the sample space and all that, because we are not trying to assign any probability to it. Maybe in one of your practice questions or graded questions, you can have the take up the probabilities function for this sample space, for this probability space, and see what properties it has to satisfy. So, you can see that later. Okay. Here is another example. Okay. So, here we will get to use a property. Okay. I promise you that. So, this is a example about a fishing town. Okay. So, in this example, you will see we will not worry so much about the sample space, we will not worry so much about writing down the outcomes or anything. We will just jump into events and work with them. Okay. We have an idea of what an event should be, and we sort of see how the probability of an event works, and there are ways to sort of estimate probabilities of events in various ways, sort of intuitive also, right. So, here is a fishing town where there are a few fishing boats that go out to fish every day, and maybe over the years people who know the trade, people who are in the fishing business have seen that the chance of catching more than 400 kilograms of fish in one day, right, they go out at night usually and then come back early in the morning. The chance that more than 400 kg of fish are caught is maybe 35%. Okay, so how would you get estimates of things like this? So maybe you keep a track of how many kilograms of fish being caught, and over the last year or so, maybe 35% of the days there was more than 400 kilograms. That sounds like a reasonable way to estimate. We'll see later on whether it's reasonable or not, but it seems like a reasonable way to estimate these kind of probabilities or chances, right? So it seems reasonable. Okay, so that's 35%. Maybe there's one more event here, which is catching more than 500 kilogram of fish. Okay, so let's call event A as greater than or greater than 400 kilogram of fish. Event B is greater than 500 kilograms of fish. Okay. So what this statement is telling you is P of A is 0.35, P of B is 0.10. Okay. So notice how in a problem like this, there is no sample space that's properly defined, or there's no notion of events, and events just show up. I mean, this doesn't come necessarily by defining the sample space and talking about subsets of the sample space. Just intuitively in practice, you just see the sample space and you sort of feel that this is a reasonable event for which you need to have probabilities, right? So you have an event A which is greater than 400 kilograms, event B which is greater than 500 kilograms. Now the question is asking you, what is the chance of catching between 400 and 500 kilograms? Okay, so what I want to know is the probability for the catch being less than or equal to 500 kilograms and greater than or equal to 400 kilograms. Okay, so this is the question that's being asked. This is the event that we are interested in. Okay. Okay. So I'm pausing here so that you get maybe some chance to think about this for a little while, or you can pause the video, of course, and think all that you want. Okay. So notice something very interesting here. So what is this event that we are interested in? It's between 400 and 500. What is this A? It's greater than 400. B, which is greater than 500. So you will notice that B is a subset of A, right? Clearly, right? So if you got greater than 500, you also got greater than 400, right? So but you can get greater than 400 without getting greater than 500. So B is contained in A, and this event actually is what, right? A must have occurred, but B must not have occurred, isn't it? I should get greater than 400. Okay, so I think maybe I should just to be careful, let me not put greater than or equal to and all that. Okay, so I'll just put it's not significant, but let's just keep it like this. Okay, so I've got greater than 400, which means A happened, but I have not got greater than 500. I've got less than or equal to 500. So B did not happen. Okay, so I put A minus B. That is this event. Now B is contained in A, and you're doing A minus B. So what is probability of A minus B? This is probability of A minus probability of B, which is 0.35 minus 0.10, which is 0.25. Okay. So here was a simple example where we had two events and we had to compute the probability of a third event, which was actually made by some complement, intersection, etc., A minus B in this case, right? So and we see that B is contained in A, right, and then we are able to simply subtract the probability of A and probability of B. Okay, so all these conditions, so this condition is crucial, right? So if this condition is not true, then you won't get this subtraction P of A minus P of B. Okay, something else will happen. Okay, so hopefully one more example which brought out the point of how you work with probability spaces and events sort of directly using the properties without worrying so much about the sample space and all that. So this kind of example is very critical. We'll use these kind of calculations over and over again. Okay, here's the next example. Okay, it's about weather forecast. Now this is something that you hear every day, isn't it? So weather forecasters always come up with these kind of numbers. And let's say one fine day you're hearing this forecast for rain and temperature. Okay, it says chance of rain tomorrow is 60%. Chance of maximum temperature being above 30 degrees is 70%. And then additionally there is one more information that is given. The chance of rain and maximum temperature above 30 degrees is 40%. Okay, so let us start writing this in terms of events. Let us say event A is that there is rain, event B is that greater than 30 degrees. Okay, this is event B. Now probability of A is given as 0.60, probability of B is given as 0.70, and what is this third piece of information? Rain and maximum temperature above 30 degrees, that is probability of A intersect B, and that is going to be 0.40. Okay. And the question that is being asked is, you have to compute the chance that there will be no rain and below 30 degree maximum temperature tomorrow. Okay, so given this detail, what can you say about probability of no rain and maximum temperature below 30 degrees? So what is the desired event here? So no rain is A complement, right? A complement is no rain. Maximum temperature below 30 degrees, okay, so maybe we will take this conveniently to be greater than or equal to, so that there is no confusion with this below, greater than, etc. So then you have B complement, which is less than 30 degrees, below 30 degrees. Okay. So you have to compute, the question asks you to find probability of A complement intersect B complement. Probability that there is no rain, A complement should occur, and maximum temperature should be below 30 degrees, B complement should also occur. Okay. So now here is an interesting fact about A complement intersect B complement. This is called De Morgan's law. It is A union B whole complement. Okay. A should not occur and B should not occur. That is the same as either A occurs or B occurs and the complement of that. Okay, neither B occurs nor A occurs, right. So this is sort of like the logical statement here, you can prove it also. This is called De Morgan's law. Okay. So this is actually the probability of A union B complement. What do we know from the complement property? From the complement property we know that this is 1 minus probability of A union B, isn't it? So I am given P of A, I am given P of B, I am given P of A intersect B, I have to find the probability of A union B. Okay. If I am done that, if once I do that, I have finished, I am done, the problem is solved. Now that is easy, I know that is easy, right. So what is probability of A union B in terms of A, B and A intersect B? I know the union and intersection property. So this is going to be P of A plus P of B minus P of A intersect B, and you can plug in all these values and compute it as 0.6 plus 0.7 minus 0.4, you get 0.1. Okay. So once again a very simple example. I have been talking about how you have to go back and forth between events and English, and this is a simple example of that, right. So you have weather forecast which gives you the chance of rain and chance of temperature being above a certain number, and the intersection also, both can happen, and then you are able to compute some very interesting thing of things like A complement intersect B complement, etc., etc. Okay. Hopefully that gave you a nice illustration of how properties are being used. So notice how the properties that we derived are being used very cleanly without any concern about, so when we did not define the probability space very properly, where is the sample space, how do you represent outcomes, is that, all that is okay, somehow weather happens every day, right. So let us assume that all that is somewhat implicitly defined, and we can work with events directly. Just knowing the properties is enough to work with events directly. So this is the last example I want to present in this lecture. So in this problem, you have been given a sample space with A, B, C, D, E, and there are two events A, B, E and B, C. These are like abstract sample space, just representations. And what all can you find with E and F, and what are all the various things you can do with E, F? So let's just try and do this sort of systematically. So you have E, A, B, E, and you have E complement, which is C comma D, right? And then you have F, which is B, C, sorry. And then you have F complement, which is A comma D comma E, okay? And then we now start doing unions, intersections, whatever, right? So you can do interesting unions and intersections. This union is not interesting. A union, E union F is interesting, right? So you can do E union F. That would give you A, B, C, E, and then E intersect F. That would give you just B. Then you can do E union F complement. That would be A, B, D, E. And then E intersect F complement, that would be A comma E, okay. Now what else can we do? You can do complements of all of these guys, right? No, or maybe we can just do the other intersection. So I finished with E. Let's do E complement. E complement intersect F. Have I done that? No. So E complement intersect F. Union F is B, C, D. E complement intersect F is just C. E complement union F complement is A, C, D, E, and then E complement intersect F complement is just D, okay. So I think this is all that you will have. I don't think you can have anything more than this. I think if you do further unions or complements or something, further complements will all be kind of closed. And if you take further unions also, I think you won't get anything new here. These are all the events I believe that you will get with all possible combinations of E and F. You can check it out. Maybe there are more fancy things you can do. I am not able to think of anything else at this point. Let me just see this. Yeah, I mean, I think anything else, you can of course make more unions and make it bigger, but I think these are good examples to start with. Maybe you can do more, right? So you can keep adding to this and see if you just repeatedly take maybe more unions till you end up in a space where you can't go any further. Okay, so maybe that's more interesting. You will get to some place. I'm just trying to see if there's anything very interesting that I can do here. Maybe not. Yeah, I think we can just stop it. Okay. So that's this example. So we saw some 4 or 5 examples. I'll urge you to look at the book and look at your practice assignments, graded assignments, and all that. And this skill is very important. Okay. So what is the skill I'm talking about? The skill of looking at a problem which talks about a probability space. Maybe events in the probability space, maybe some of the probabilities, maybe some manipulation of the events. And typically the probabilities and everything is probably given in English, right? So it'll say chance of rain tomorrow, etc. So can we do something interesting in that probability space? Can we write down those events? Can we think of other events that are obtained from that event? Can we find their probabilities, etc., etc.? All these things are very interesting, simple problems, and it's good to practice these kind of problems as much as possible. I'll encourage you to look at the book and also the practice and graded assignments. Okay, all the best.